Hello, so today we are going to do this problem which is part of Leetcode daily challenge, search 2D matrix. So basically we have an m by n matrix and it has the property that it's sorted in increasing order, and the first basically integer of each row here, except the first row of course, is bigger than the last element of the previous row. So 10 here is bigger than 7, 23 is bigger than 20. And the goal is to return true if target is in the matrix, otherwise we want to return false. Okay. And what this property basically tells you is that the matrix is sorted. Just like you can see here, it's sorted. Basically, if you put each row after the next, it's sorted. So it's sorted like this, then like this, and then like this. And 7 here is smaller than 10, and 20 is smaller than 23. And the length you can see here is not too big, it's 100. So this tells you, the length being 100, it tells you that you can even do like a no-event squared solution. So something where you just go through the row and each value in the matrix and just look for the element, right? But that's not really what they are, not really the ideal solution, because also they ask us to write a log m by n time complexity solution, and that solution of looking at each element is of m by n. Okay. And also we didn't take advantage of the fact that the matrix is sorted. So how do we do it for the case where the matrix is sorted here? Okay, so how can we tackle this? Well, we want binary search, so as I always approach these problems is with trying to find a monotonic function. By that I mean a function where it's first either always false, and then when it starts becoming true, it stays true all the way to the end. Or it starts becoming true and stays false all the way to the end. So you need to find one of these. And in this case, we can just find this. So what we are looking for? We are looking for the first value where it's bigger or equal to target. So we are looking for the first value where f of x being the position of that element where it's bigger or equal to target. That way, this is the first true. It's either target is either here or it's not in the array. Okay, so that's the idea of what we are looking for. But the problem is, what is this f of x, right? So ideally we want a way to say, we want a way to have this f of x maps to some value in the matrix. But how do we get these I and j? And that's where the clever idea is. You can just think of this matrix as if it was a single array. So just think of it as if it was 1, 3, 5, 7, and then the second row 10, 11, 16, 20, and then the last row which is 23, 30, 34, 60. So the idea here is think of it as if it was just one single array. Then in that case, f of x would be, and this is the array, would be just a of x bigger or equal to target. Okay. And so what would be the search space? Well, it's from this position 0 to this position. Now what is this position? Well, this matrix is rows by columns, elements. So this position is just going to be rows by columns minus 1. So we just need to search in this space from this index to this index and find the first element where it's bigger or equal to target. So the first true here. Now the only thing remaining is, okay, how do we map, then do this mapping here? And that's where it's very easy, right? Because let's say in this range you are looking for this element, position 16 here. How do you find, you know, its position is going to be in the array representation, its position is 6. How do you find its position in the matrix here? So the matrix, this is 0, 1, 2, 3, 0, 1, 2. Well, it's pretty easy. You just divide by the number of columns to get the row index. So if you take 6 divided by how many columns we have 4. Okay, so if you do 6 divided by 4, that tells you it's 1.5. So that tells us we are in row 1. So we know it's in this row. Because if you divide by the number of values in each row, you will get the row index. That just makes sense, because when you divide by the number of elements in each row, you will get how many rows up to that element, which is the row index. And then now that we know that this is the row, how do we know which position? Well, we know that it's this row. Then we can just take the modulo, because if you take the modulo of the number of elements in each row, you will know how many remaining elements, right, at the last row, right? How many remaining elements after we remove the other rows. Okay, I hope that made sense. If it didn't, just sort of try to write it down on some examples. It would be easier, but also this is just how it works with the indices, mapping the indices from matrix to an array. So if we do 6 modulo 4, that's going to give us 2. And so that means this is index 2, which is this element here. And now we are done, okay? And so this is how we will map then. So the mapping is going to be just, if we get the index in the map, let's call it, that's what we'll get with mid. Let's call it, for example, x. Then to get I and j, is just going to be I is x divided by the number of values in each row. So it's the columns, the number of columns, right? This column, this column, this column, this column. And j is going to be just x modulo column. Okay? And so now we can just write the default binary search that we usually do, where now we know the bounds that we need to work with, 0 to rows by columns -1, and we just need to think of f of x as array of x, and that array of x we can map it to the matrix using this formula here, and check if it's bigger or equal to target. If it's bigger or equal, we know we are in the true range. If it's smaller, we know we are in the false range. So when it's smaller and we are in the false range, we need low to always be false, so we set low. When it's true, we want high to be always true, so we set high. That's all you need for binary search. Now, what's the time complexity for this? Well, the time complexity is O of log of the search space. Now, what's the search space here? Well, it's just the elements, number of elements here, which is rows by columns. And this is exactly what the problem asks us to do, which is m by n, m being the number of rows and being the number of columns, and log of those, right? That's what we are being asked, and that's what the final solution is. Now, just to reiterate, we were able to do this binary search because when we convert this to an array, it's a sorted array. That's why we are able to do binary search here, because that being sorted gives us this property that once it's true, let's say it's true at 6, bigger or equal to target, then if you go right, you will only increase values, so it will still be bigger. And so that's why we have true here. Okay. Now let's write it up and make sure it passes. Okay, so let's write this binary search. So first we just need the rows and columns in the matrix, right? So that's like this. And then now what's the search space? Now, one rule here with these types of binary search, to just avoid any problems in case you have only false or in case you have only trues, just pick a low and high values that are out of the range we are searching in. So the range we are searching in is from 0 all the way to rows by columns -1. So let's just pick the bounds that are before these values. So before 0, that's -1 for low. And just after high, so outside of the bounds there, it's going to be rows multiplied by columns. And we'll keep going. Remember, our function is like this. We'll keep going when low is here and high is here. So there is difference of just 1 between them. Because remember, we want the first true. That's what we want. So that's what we do this. And now we want to get the mid, which is going to be just low plus high divided by 2. We can do division by 2 using binary to avoid overflow. And now we just calculate I and j with the formula that we saw in the overview. So I is going to be divided by the columns, the number of columns, and j is going to be modulo columns. Okay, and now we just check if f of x is true. We said that f of x is going to be just the matrix of I and j, and we want to make sure that it's bigger or equal to target. That's what, so this basically means f of x is true. So we want to maintain that high only is always true. F of high is always true, and f of low is always false. Now, since this means that f of mid is true, then we want to set high to mid, because this means that the value mid, the function is true. And so we are either here or we are in the first true. So in case we are in the first true, we want to set high to be equal to mid, because we are only interested in true values for high. Now, if it's false, then to maintain this invariant, low still needs to be false. So we keep low at mid, because f of mid we determine that it's false. Now, in this case, either mid is the target, high is the target, so the element at high is equal to target. In that case, we want to return true. Otherwise, we're going to return false. Okay, so we need to check if it's equal to target, because maybe we are in this case where we only have false values. And so to do that, we want to check, again, we want to calculate the I and j for this high, because remember, high is in the imaginary array that we create out of this matrix. We don't actually create it, but we just represent it out of this matrix. And so it's going to be just the same way we did for mid here, except instead of mid, we want to use high. Okay, and we want to check, we want to return true only if the matrix at that position is actually equal to target. Okay, but we also don't want, if let's say high we didn't find, it's all false values, so that means high is rows by columns, it didn't change. Then in that case we want to check also that high is actually within the range. Okay, so for this to be true. And so once we do these two, and I think what's the problem here? Sorry, this needs to be multiplied like this. Okay, so let's submit, and looks like this got accepted. And yeah, that's pretty much it for this problem. Pretty straightforward binary search. The main idea here is to sort of represent it when you are doing your solution in terms of an array, and we'll get a sorted array so we can apply binary search. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.